So more on radicals. So basically these are the sections 7.3 and 7.4. They're talking about multiplying, dividing, simplifying radical expressions. They're kind of talking about the same thing across the board. 7.3 is multiplying, 7.4 is dividing. So we'll just talk about them at the same time. So we ended Monday's class with realization that a to a fractional power is really a radical. That was one of the things we realized closer to the end of the Monday's class. And in more general, we had this realization that a number raised to a fractional power gives us another radical where denominator is the index of the radical and the numerator is the exponent. Or, equivalently, we can take the exponent all the way on the outside. So it's either everything raised to the power m or just a raised to the power m. It doesn't matter which one you do first, root or the power, you still get the same answer. It is easier to do the root first. And we had one of the examples on Monday. But anyways, since radicals are exponents, really, so they behave like exponents. So they have very similar properties, like exponents do. So for example, we had all those rules of exponents on Monday. So we had these two rules. A times b to the power n equals a to the power n times b to the power n. Remember that? That's one of the rules of exponents. So therefore, the nth root of ab is the same as the nth root of a times the nth root of b, and so forth. So we can do that. We can distribute the radical through a product and vice versa. A product of two radicals that have the same index can be pulled together into one. And you kind of use that already. We realized that on the packet. We had to go square root of 2 times square root of 3, and we'll agree that will be square root of 6. Right? So this allows us to simplify radical a little further. Because I can give you, if I ask you what is a square root of 36, you will not have any problems with that. You will tell me 6. And if I ask you what is the square root of 5, you will tell me square root of 5. There's nothing you can do with that. So these are the two extreme cases. One is a square root of a perfect square, and one is a square root of a number that's very far from being a perfect square. But there is a middle ground in these types of exercises, and that's if I, let's say, ask you to take a square root of 20. Is 20 a perfect square to begin with? No, but can we think of 20 as a product of a perfect square and something else? 4 times 5. 4 is a perfect square, so I can apply this product rule. So I can take the square root of 4, right? I mean, I don't have to write it, but really what is happening is the square root of 4 times the square root of 5. So square root of 4 is 2, and you're left with the square root of 5. So we can do that to mixed numbers like that. We can simplify them a little bit. So your book kind of being very nice to you, but I'll try to do the same. How do we treat square root of 32, for example? Well, 8 and 4, so 4 is a perfect square. But you start with the 16. I like that better. 16 times what is 32? 2. So both kind of work. 8 and 4, 16 and 2, both contain a perfect square, but then you'll be stuck with the square root of 8, and you have to deal with that as well. So given options, always go for the largest perfect square that goes into the number. So the correct way of doing this one would be 16 times 2, so square root of 16 is 4 square roots of 2. And that really means 4 times the square root of 2. Okay, so yeah, that's as far as I can go simplifying this expression. For example, if I give you square root of 81a, well, I don't know what a is. A is a. I can definitely take the square root of 81. That becomes 9. A doesn't go anywhere, so it's still under the radical. How about square root of 50a squared? Yeah, so you think of 50 as 25 times 2, and then you still have the a squared. 25 is a perfect square. A squared is a perfect square. I can take square root of them. So what is the square root of 25? And what is the square root of a squared? What was that? Yeah, but you still have something left. I was sure. It's just a. For those of you who were here on Monday, if you take a square root of a squared, what's it going to be? No, that's not what your notes suggest. What does it say in your notes? Eric, you don't have this in your notes. You missed that part. The absolute value, but you have to make sure that the answer comes out positive always, because there's no guarantee that a is negative at the beginning, because it doesn't matter, because you're squaring it kills the negative anyways. So we kind of talked about that. We have to be careful. I'm sorry, we're talking both at the same time. Go ahead. I mean, that would be the correct way of doing this problem then. Yeah. So part of the definition of the square root that it always comes out positive. Okay? So what I mean by that, if we just, for example, if I had square root of, and we were playing with this example, so let's say square root of whatever this is, 13 squared, then it's 13. But if I give you the square root of negative 13 squared, it should still come out as a positive 13. And again, by the order of operation, you square negative 13 and becomes positive. And then you take the square root, so it's still positive 13. But if I just simply drop the powers, it comes out negative 13, right? If I just ignore everything else, just, okay, square root kills the square, so I'm left with whatever this number was. So that's why we say we'll introduce the absolute value, and it will always guarantee that the answer comes out positive. Well, if it's a number, then you can kind of do this in your head. 13, 13, negative 13, still 13. Well, yeah, you'll give me the right answer regardless. But with variables, you have to kind of make sure that the answer comes out positive regardless. And this is the way to do that. Okay. Now, your book is being really, really kind to you. So before every exercise, they say this phrase, which is just, I don't know, it's too nice. It says phrases like this: assume that, okay, no, never mind. Okay, assume that no radicants were formed by raising negative numbers to even powers. So you just assume that everything is positive, basically. So you don't need the absolute value, but as far as your book is concerned. Unless they don't say that phrase, unless they don't say assume that all variables are positive, then you have to get all absolute value happy. But if they tell you off the bat, assume everything is positive, then you're in a good shape. And it says almost everywhere. Unless, hang on a second, unless you're dealing with functions, it won't say it with functions, so you have to kind of be careful, I'll do examples of that. But almost on every other exercise, they say assume everything is non-negative, so we're good. Yeah. No, it it was I don't remember. Yeah, that's the absolute value. Um, so anyways, um, so if I tell you assume that all variables are non-negative. If I tell you that, then you don't have to worry about absolute values at all. I can give you, I have too many pages here. Let's say I can give you this example to play with. Simplify. And let's say I have a square root of 9, a to the power 7, b to the power 5. Now, another side note, as far as all this negative positive thing goes. A and b cannot be negative to begin with in this expression because of the odd exponents. If a is negative, a to the 7th power will still be negative, and then you're stuck with a square root of a negative number, so that's not good, right? So when you see odd exponents, it just has to be positive to begin with. So this is why your book actually specifically mentions even powers. With odd powers, you kind of have to realize it has to be even, I'm sorry, it has to be positive in order for this to work. But anywho, let's play with that. 9 is a perfect square, right? We can take the square root of that, no problem. But how about a to the power 7? Is a to the power 7 a perfect square? No, right? Now, because we understand when we take the square roots, the square root is equivalent to dividing whatever the power is by 2, right? Based on this rule, it tells you when you take the square root, it's the same as dividing the power by 2. So basically, we're looking for even powers. Every even exponent is a perfect square. So what is the largest perfect square, then, that goes to the a to the power 7? What was I asking? I never said anything like that. So before we were taking a number and we would split a number into a product of a perfect square and something else, right? And then we'll take the largest perfect square, like with a 32. We went 16 times 2. 16 was the largest perfect square that goes into 32. So we're able to handle that, right? Now, this is a little different. This is a to the power 7. Do you all agree that that's not a perfect square? Why is that not a perfect square, if you agree with me? What? Well, okay, let me write a few things here. 18, a to the power 12, 9, 25, a to the power 5, a to the power 7, and I don't know, 72. So I have 1, 2, 3, 4, 5, 6 expression. Is this one a perfect square? No. And why? Just kind of give me a simple answer. Okay. Or there's no number, no integer square gives you 18. How about a to the power 12? Is that a perfect square? What? Yes? Why? Even, because what squared equals a to the power 12? What do I need to square to get a to the power 12? What? 6. So every time you see an even power, that's a perfect square, because the 12 itself does not have to be a perfect square, it just has to be even. So 9 is a perfect square. How about 25 a to the 5th as a whole? Is that a perfect square? No, because of the little power 5. That's an odd exponent. But how would you split it up into a product of a perfect square and something else? 25 is a perfect square, right? So we're okay with that. How would you split a to the 5th so it's a perfect square times whatever's left? What? Well, 5 and 1 will give you 6. Yeah. What? Yes, I'm not arguing that. But what do you do with exponents when you multiply? Add them. So then 5 plus 1 is 6. Right? I mean, if you write it as a times 5, and then a, this is no longer a to the 5th. This is a to the 6th. Right? Okay, a squared times a to the 3rd, is that the largest perfect square that you can pull out of a to the 5th? A to the 4th is the largest one. So you can always kind of borrow one. A to the 4th and 25. That's the perfect square. Then you have a little a tagging along. So basically you're just trying to get your exponents to be even. Is a to the 7th a perfect square? How would you split it? A to the 6th times a, right? So you can take the square root of a to the 6th. You cannot see the 6. Well, you can take the square root of a to the 6th. You'll get a cubed. And that stays outside the square root. So you're done with that one. Is a to the power 72 a perfect square? Yeah, because then again, all you have to look for is the even power. Is a to the power 72 a perfect cube? Probably. What do you think? So the question is, can you write a to the power 72 as something cubed? And since we multiply exponents, really the question is 72 divisible by 3? That's really the thing. Is 72 divisible by 3? Yeah. What's left? 24-ish? Yeah, so this is a to the power 24 cubed. So a to the power 72 is a perfect square. It's a perfect cube. It's probably a perfect 4th power, because 72 is probably divisible by 4. 4 times 18, 72. So basically, the exponents have to be divisible by the index in order for them to be perfect, whatever that index is. Perfect cubes, powers divisible by 3. Perfect 7th powers, so the powers have to be divisible by 7. Because when you take the roots, you're really dividing powers by the index based on that first thing that I wrote. So how would we rewrite a to the power 7? So it contains a to the 6 times 1, so a to the 6 times a. How about b to the 5th? B to the 4th times b. So now I can take the square root of 9. Square root of 9 is 3. I can take the square root of a to the 6th. What would that be? A cubed. You're just dividing the powers by the index. And in this case, it's 2. What? Well, because it's a square root. We don't write a little 2. We assume it's a square root. It's playing with the 2's. For every other root, we put a little number there. But for square roots, we don't. Right? I mean, you knew that. You know that that's a square root that plays with the second powers. Right? How would you take square root of b to the 4th? B squared. Then everything else stays, so you have a and b still under the square root. Okay? Here's another example, a square root of 75x to the power 8 and then y cubed. Again, assume that everything is positive and so forth. So with 75. Is 75 a perfect square? Sorta. How would you split it? Yeah, but none of those. Really? No, 13 times 5 is 65. 25 times 3. No, 13 times 5 is 50 plus 15, so it's 65. Right? What? Okay. So 25 times 3 is x to the 8th power perfect square? Yes, because again, all you look for even exponents. How about y cubed? Is that one a perfect square? 2 and 1. So y squared times y. So we can take the square root of 25 comes out as 5. We can take the square root of x to the power 8, comes out as x to the power 4. And then we can take the square root of y squared, comes out as y. And then we still have 3 and another y under the square root. Well, good question. The answer is, regardless of this story, you see, even if I tell you that, then yeah, don't worry about the absolute value. But even if I didn't tell you that, see what happens. Well, okay, x to the power 8. So x potentially could be negative, right? I mean, and you raise a negative to the power 8 and it stays positive. But when you took the square roots, it still has the 4th power, so it doesn't matter whether x is positive or negative, the answer still comes out positive. But with the y's, originally we had y cubed. So in order for this to work, y has to be positive to begin with. Does that make sense? So the absolute value here would be redundant. You don't need it regardless of the case. So I think this is why the book took it easy on us. They decided, so it's too much extra analysis to perform. Just assume it's all positive, so don't worry about that. We're only going to worry about the absolute value when we're dealing with functions. So here's an example of what I'm trying to say. Now I have the set of exercises that says find a simplified form of f of x. Assume that x can be any real number. So this is where we have to be kind of careful. We have to pay attention to the absolute values and so forth and so forth. So here's some examples. F of x equals a cube root of 40x to the power 6. Now with the cube roots, we don't worry about absolute values at all because of the odd radical. Remember we talked about that? Even radicals have to come out positive no matter what. Odd radicals can come out positive or negative. So every time you see a cube root, a 7th root, any odd root, no absolute values at all regardless of what's going on. Because answers could be negative. That's okay to have a negative answer. So, is 40 a perfect cube? But what times what equals 40, where one of the items is a perfect cube? 10 and 4? Well, none of those are perfect cubes. 8 and 5. 8 is a perfect cube, right? So I really want to split 40 into 8 and 5. Then I can take cube root of 8. How about x to the power 6? Is x to the power 6 a perfect cube? Again, it just has to be divisible by 3 then. Yeah, so it is a perfect cube, right? If this exponent is divisible by that number, then you have a perfect situation. Because that's what that rule tells us. You just divide exponents. So we're just going to leave it be. So we can take cube root of 8, that's 2. We can take cube root of x to the 6th, that's x squared. And that leaves you still with a cube root. Okay, that looks weird. It looks like I have power 23 there. And I still have a cube root of 5. So that's that function in a more simplified version. We took cube root of 8, gave us 2. We took cube root of x to the whatever 6, gave us x squared, 5 stayed. And don't need to worry about absolute values because of odd radical anyways. Okay, let's try this one. Cube root of 27x to the 5th. What? Well, it's just a function. Yeah, so I'm calling those functions. Those are functions, some radical functions. I can graph them if I was in a really good mood. Well, but is 27 a perfect cube to begin with? Yeah, but that's not how you take a cube root. You don't divide by 3. If I ask you to divide by 3, I would just say divide by 3. This is a different operation. Is 27 a perfect cube? Yeah, what cubed equals 27? 3. Okay, how about x to the power 5? Is that a perfect cube? How would we split it? 3, well, 3 and 2. You want to have something that is divisible by 2. What was that first one we did? It was 40x to the power 6. And then we're taking the cube root. I don't have a cube root button, but I can do power 1/3. That's cube root. And I can probably plot that thing. Looks kind of like a parabola. Is it going to get all weird on us? Oh, yeah, it won't get weird on us. Right? That's the graph. And then when we simplify that, we got what? We had 8x squared, right? So that's a parabola times, we had a cube root of 5. So cube root of 5 is just some constant. So it doesn't do anything else. We're going to get the same exact graph. Yeah, get out of here. Did we get the same exact graph? Why did I do 8? It should be 2, not 8. Here we go. So these are 2 of the same functions. If I get rid of that one, I'll just have that one left. So anyways, sorry, a little sidetrack. Yes, 27 is a perfect cube. And x to the 5th will split it as 3 and 2. Because again, since the cube root, you want the powers to be multiples of 3. So then we can take the cube root of 27, that's a 3. Cube root of x cubed is just x. And then you still have a cube root of x squared left. Well, cube root of 27 is 3, because 3 cubed is 27, right? And again, if I play with foo plot on that one, what was the original thing? It was 27x to the power 5, and then cube root of that. So, yeah, well, that's a fun-looking thing. Just half a parabola. What is that? Okay, foo plot is not. Foo plot is wrong. Yeah, anyways. It's wrong. Because I can have negative numbers in there. Okay, how about this one? Now again, we're dealing with functions, so any value of x is possible. So square root of 49 times x minus 3 squared. Because think about the domain of this function. Remember, when we talked about the square root, this is a square root now. The radicand cannot be negative, right? Because if you take a square root of a negative number, it's not a real number. So we played with domains of square root functions on Monday, and we were just setting the radicand to greater than or equal to 0, and we're solving for x or whatever. But since I'm squaring my x's here, no matter what, the square will make everything positive, right? So then I can take the square root of that. So the domain of this function is all real numbers. No matter what I put for x, the square will make it positive, and then I can take the square root of that. So x could be positive, x could be negative. So in this case, I have to be careful. I have to use the absolute values because I need to guarantee that the answer comes out positive. So 49 is a perfect square, right? The square root of 49 is just 7. And then when I take the square root of something squared, all I have to do is to toss the absolute value around x minus 2. So this guarantees that the answer comes out positive. Minus 3, yeah, that's just me being silly. Yeah. So that's not the issue here. 302 is more of the absolute value. So this makes sure that whatever you put for x, the answer comes out positive every time. Because I want these two functions produce the same results. Okay? For example, just for example, if I put x equals negative, I don't know, 4. No, 5. So if I put it into the first function, it's a square root of 49 times negative 5 minus 3 squared, right? Which is a square root of 49 times negative 8 squared, right? That's the order of operation. You with me so far? The square root of 49 has to come out to be 7, right? Negative 8 squared is positive 64. Square root of 64 is 8. So the answer is, I'm not sure, 56 maybe? 7 times 8? Is that 56? Irrelevant. I mean, positive number, right? Now, if I put negative 5 in there, I have 7 times absolute value of negative 5 minus 3, which is 7 times absolute value of negative 8, which 7 times 8, which is 56, right? So that makes me happy. We get the same answers. If I don't have that absolute value, I'll get answer of negative 56. That's not the same as my original function, so therefore that equal sign would not be true. So that's why we need the absolute value to make sure answer just come out positive. So that's really, your book only leaves that pain in the ass for the functions. Only when dealing with functions, the book will say, assume that x could be just any real number, so suck it up and do the absolute value properly. Well, okay, good question. Let's try this example. F of x equals, let's say again, the square root of 5x squared minus 10x plus 5. So it looks like a pretty bad situation. But let's do some factoring. Okay? And you'll see how this is answering your question, by the way. Can I do some factoring with this 5, 10, and 5? Is there a common factor? 5, so I can pull a little 5. Still, everything is under the square root. So x squared minus 2x plus 1. So we did that little bit of factoring. Now, can you factor x squared minus 2x plus 1? Is that factorable? Yeah, what does that equal to? So x minus 1 squared. So when you factor, that's a perfect square trinomial, you're left with the square root of 5 times x minus 1 squared. just factoring. I'm not really paying attention to the fact that I have a square root there. I'll just keep copying the square root. I just did a bunch of chapter 3 or whatever chapter that was, style factoring, right? Well, now, square root of 5, is that a perfect square? No, and there's nothing I can do with 5. 5 is not going anywhere. But x minus 1 squared, I can take the square root of that. I have to use the absolute value to make sure the answer comes out positive. So the answer here would be square root of 5 times the absolute value of x minus 1. How's that? No? What? Well, then it's that deserves a, I don't know what. No, I think she's stuck on the factoring part. Yeah. So you either factor it old school way, or you recognize this as a squared minus 2ab plus b squared, and it's a perfect square trinomial. That's one way to look at it. Or two numbers that multiply to 1 and add to negative 2, negative 1 and negative 1. So, I mean, you should be able to factor. Okay. So these are these. So this is, again, the only time where your book makes you pay attention to the absolute value. And I'll do the same way, the same thing. Unless we're talking about the functions where we'll tell you x is any real number, then pay attention to the absolute values. Most of the time, it will just say assume that everything is positive, or assume that the even powers have positive bases. Because the odd powers must have positive bases in order for the square roots to work. Anyways, let's try this few exercises. Again, simplify. I'll do square root of 2 times the square root of 6. Well, none of those are good news, right? Square root of 2, not much you can do with that. Square root of 6, 6 is 2 times 3, nothing much you can do with that one. But, again, as the earlier mention of the properties similar to the exponents, I can push them into the same square root. Square root of 2 times square root of 6 is square root of 12. Only works if those are the same radicals. If it was square root of 2 times cube root of 6, then you're kind of done. Nothing much you can do with that. But that gives me a square root of 12. Can I deal with that one? Can I simplify square root of 12? Yeah, since 12 is 4 times 3, 4 comes out as 2, square root of 3 stays. Is that okay? We can do it the other way, actually. There's another way of thinking about this. Square root of 2 is square root of 2, and the square root of 6, well, it's 2 times 3, right? So that's really a square root of 2 times square root of 2 times square root of 3. If I split it up all the way to the basics. And what do you think a square root of 2 times square root of 2 equals to? 2, because that's square root of 2 squared, right? So you still get the same answer, but I think it's a little messier if you split it up rather than pushing them together and then doing that. Because we kind of got lucky there. About this, square root of 6 times square root of 33. Well, that's a big mess. Maybe we should. Yeah, we can do like that. But now, I really probably have to do a little bit of both here, because I really don't want to multiply 6 by 33. What is that? 198, right? What on earth is 198? Right? I mean, what is 198? Well, first of all, not a perfect square, right? 198 is divisible by 3 because we got it from 3's, and then also divisible by what? I mean, it's a weird situation. Well, that's the thing. If it was 200, it would be a little easier to play with, but it's not, right? It's 198. So that's one that's hard to deal with. So maybe it is a good idea to maybe break it, instead of multiplying the large number, break it down into small numbers. What is 6? 6 is 2 times 3, right? And what is 33? 33 is 3 times 11. Maybe this is easier to split it up into a perfect, into the primes, and then you see, well, I have 3 times 3, right? I can take the square root of that. That's 3 squared, or 9, or whatever you want to call that, right? I can take the square root of that. It will come out as a 3. Do you agree with that? This is a 3 squared, or whatever, so you have 3 on the outside. Well, 2 and 11, they're 2 prime numbers. Nothing you can do with that to simplify. So 2 and 11 will both stay there, so it's 2 times 11, 22. They're not going anywhere. 2, 11, 2 primes, no perfect squares, we're done. Otherwise, you have to go 198 clearly is 9 times 22, which is hard to see, and then you take the square root of 9. But it's easy if you break it down and you see all the common factors. So you have 3 squared here, and you go bam. Actually, this is how you can take square roots of really large numbers, by doing prime factorization, and then see what the exponents are. Maybe we'll do one of those. Do I have one of those? This is really fun. I don't have one of those. Okay. So again, so we understand how to multiply them. We're going to talk about how to divide them. Adding, subtracting, just a quick. And again, you kind of played with that on Monday a little bit. When you add, subtract expressions that have radicals, you're just thinking about combining like terms. So you can add square root of 5 to square root of 5, and you can add square root of 7 with square root of 7, but you cannot add square root of 5 with the square root of 7. Those are 2 different expressions. So if I have something like this, I ask you to simplify 2 square roots of 3 plus 4 square roots of 3 minus 3 square roots of 3, and then minus another little square root of 3. You just do this like combining like terms. You're treating just what? 2 square roots of 3? Okay, so 2 square roots of 3, right. So you're just combining like terms. 2 plus 4 minus 3 minus 1 is 2. It's not over, it's 2 square roots of 3. Just there's no over. Yeah, so think of this, it's the same as 2x plus 4x minus 3x minus x equals 2x. It's the same thought process of when you're combining like terms as when you're adding similar radicals. Do you see that? So again, the question is how many square roots of 3 you have in the end, and that's 2. So these are kind of equivalent. If I give you 5 square roots of 2 minus 3 square roots of 5 plus 2 square roots of 2 plus 5 square roots of 5, you can add the square roots of 2, you can add the square roots of 5, but you cannot add them across. It's like having 2 different variables, x and y. So how many square roots of 2 do we have? 7, right? It's 5 plus 2 gives you 7. So that's 7 square roots of 2, and then for the 5 we have -3 and a +5, 2. So plus 2 square roots of 5. And that's as far as you can go. There's nothing else you can do with that expression. That is your answer. We cannot add square roots of different radicals. Just like with the, x squared and x cubed, we cannot combine them. Or x squared and y squared, we cannot combine them. Is that okay? All right. How about this one? So these two radicals are very much different, but I can do something first. Can I simplify square root of 32 as it stands, and can I simplify square root of 50 as we did earlier today? We're thinking of 32 as 16 times 2, right? That's how we split 32, and I can take square root of 16, gives me 4 square roots of 2, right? And I can split 50 into 25 and 2, so that is 5 square roots of 2. Now they have the same square root portion, so I can add them together. Looks like 9 square roots of 2. 4 plus 5. So, after we simplified them, we realized that they do have the same radical. So there are like terms, so you can combine them. It's 4 roots 2 plus 5 roots 2 is 9 roots 2. How's that? Okay. So again, just think about combining like terms. So division, we have, again, just like with the rules of exponents, if you have the nth root of a function, of a fraction rather, nth root of a over b, it's the same as taking nth root of a numerator over nth root of a denominator. And again, we kind of saw that on Monday. And you have the rule of exponent just like that. If you take a fraction to a power, you raise the top to a power and the bottom to a power. So if I ask you to simplify something like this, a cube root of 16x cubed. Why did I go for the cube root? Now, okay. Over y to the power, 12. So basically it's the same process as with products. You just have to take a cube root of each little part. Here's x cubed, a perfect cube. Yeah. How about y to the 12th? Yes. How about 16? No. Right. How would you split 16 into a perfect cube and something else? 8 and 2, right? So really we're going to think of 16 as 8 times 2 x cubed over y to the 12th. And then we'll take a cube root of each portion. Cube root of 8 equals 2. Cube root of x cubed is just x. Cube root of 2 stays, doesn't go anywhere. Over cube root of y to the 12th is y to the 4th. So you're just dividing all powers by. How is that? Yeah, but it's same as multiplication, only you have a fraction there. Well, how about this one? Let's say I have a fourth root of 18 a to the power 9 b to the power 5 over a fourth root of 3b. Nine. That's a ninth power there. Okay, that didn't help. 9. Apparently I cannot make 9s today. So in this case, it's actually beneficiary to push it under the same radical. This is the same as the fourth root of 18 a to the power 9 b to the fifth over 3b, because I can reduce this fraction, right? Because again, this rule allows me to go either way. It's a ratio of the roots equals one root, or one root equals ratio of the roots. So I can certainly reduce this. 3 goes into 18 6 times, and b goes into b to the fifth 4 times. So we're left with a fourth root of 6a to the power 9 b to the power 4. Is that okay? So 6, nothing I can do with a 6. No matter how I split it, I won't be able to take a fourth root of it. How about a to the power 9? 8 and 1, right? Because you want to have powers divisible by 4, and b to the fourth, we're good with it. So we're going to split a to the power 9 as a to the power 8 times a, and b to the fourth is already a perfect fourth power. So I can take the fourth root of a to the 8th power, gives me a squared. You're just dividing the powers by 4 now. B to the fourth turns into b, and we still have a fourth root of 6a. Yeah, so this is still, yeah, this is the step. This is still a to the power 9. And the reason why we chose 8, because 8 is divisible by 4. If this was a to the power 11, we would still split it as the a to the power 8 and a cubed. You still want to get the divisible by 4 numbers because of the fourth root. How's that? Yeah? Well, yeah, there's nothing else I can do with it. Oh, no, that's messy. Because think about this. These are much smaller powers. Here I would have to raise something to the power 9. That's huge. I don't have to do that here. I can just square it. Now it's easier to work with. How about this one? 100 AB under the square root over 5 and the square root of 2. We're not ready for this question yet. But anyways, what can we do? Well, no. Order of operation, I cannot divide 100 by 5 when 100 is under the square root. I see, because the square root is the same. Square root is the equivalent of a power, so you do square roots before division. In the order of operation, the square root takes place of the exponents in the PEMDAS. Hang on a second. Yeah, we can do that. Now, what were you saying? Yeah, we can do like we did the last problem. If I just, that 5 doesn't go anywhere, so I kind of have 5 it's kind of weird, but I have a square root of 100 AB over 2, and then I still have kind of 1/5 on the side. We can kind of do that because that 1/5, that 5 was not a part of the square root. So you can reduce this. It's 1/5, and then what is it? Square root of 50 AB, right? You divide 100 by 2. And then how do you deal with the square root of 50? Where? 25 and 2, but where did I lose you? Where did I lose you? Well, the 5 is not in the square root, right? So if I were to combine the square roots into 1, I still have to show that I have 5 in the denominator somewhere. I cannot put it inside the square root, right? So it has to be outside the square root. Well, 5 is in the denominator, so it's 1/5, right? Yeah, because 5 was already outside. I can push it inside. Well, we'll talk about this in a second. There are a few ways we can do this one. But yeah, so 50 is 25 and a 2, so it's 1/5 times 5, and we still have 2ab under the square root. Right, I can take the square root of 25. Comes out as 5, so these two cancel. Square root of 2ab. That's another way. There are really many ways of thinking about this problem. So this whole confusion at the very beginning, I'm going to do it in different colors. The 5 was on the outside of the square root, right? So it's just 5, a normal, friendly 5. And we dealt with examples where the numerator was just a radical and the denominator was just a radical. Here we have a numerator is a radical, while denominator does have that integer portion to it. Now, it probably would be easier on the I if this was my problem. Just big square root on the top, big square root on the bottom. So the question is, well, can I push 5 inside that square root? What do you think? If I can take a number on the out from the square root, right? If I have 25 inside the square root, when it comes out of the square root, it turns into 5, right? You know, we did that before. If I have 25 times 3, that is 5 times square root of 3, right? So if I have 25 on the inside, it comes out as 5 on the outside. So then if you have a 5 on the outside, if I want to push it inside, you square it. So whatever the root was, if it was a cube root, you will cube it. If it was a 10th root, you raise it to the power 10. So if 5 goes back in, it becomes 25 times 2, which is a big square root of 100 AB over 50. If you push that 5 inside the square root, it gets squared. And then you reduce your 150, you still get a square root of 2ab. So you still have the same answer. Right? If you go from the square root, you take the square root. If you go back in, you have the square root. Same answer. Now, Austin was saying right off the bat, well, why don't I just go ahead and just take the square root of 100? 100 is a perfect square, right? That's what you were saying. And that's okay. If I start with this problem, 100 AB over 5 square roots of 2, I can take the square root of 100. it comes out as 10 square root of AB over 5 square roots of 2, right? Just taking sort of 100 comes out as 10. And I can reduce 5 and 10, can I? Because again, these are products. 5 square root of 2 is 5 times square root of 2. This is 10 times the square root of AB. So 5 goes into 10 twice. So we have 2 square roots of AB over the square root of 2. Right? What? But do we get the same answer? Right? This looks different from that. I'm sorry, this looks the same as that, okay, but different from that. And the difference is, here I just have a square root of 2, and here I have a 2 divided by the square root of 2. Right? Yeah. Yeah, but one of them is still a little more polite, but square root of 2, right? This is the constant in front of the previous two answers. Do you agree with that? This is the coefficient. I can compute the square root of 2. Square root of 2 equals whatever that is. Okay? You know, 1.41, whatever. Irrational number, ugly, all that good stuff. Now, the coefficient in front of the last answer is 2 divided by the square root of 2, right? Well, let's see. What is 2 divided by the square root of 2? Well, it's the same thing, okay? So really, the square root of 2 is the same as 2 divided by the square root of 2. They are numerically equivalent. Now, one of these answers is more acceptable than the other. And we'll talk about this in a minute. We generally don't like to see radicals in the denominator. I mean, it makes your fraction, I mean, you're already not big fans of fractions to begin with. Now, it makes this fraction even worse. It makes the denominator irrational, so go ahead, try to add some fractions like that. Finding the LCD is going to be pretty messy. So we don't like having square roots or any types of roots in the fraction. So we're going to go through the process of what we call rationalizing the denominator, getting rid of that square root from the denominator somehow. And we'll talk about that in a minute. But numerically, these three answers are the same. You put them in my math lab, I can probably bet that you'll be marked wrong for that one because you have the radical in the denominator. You'll be marked correct on another one. Don't get mad on my math lab. On the exam, if you leave the answer with the square root of 2 in the denominator, you're still going to be marked wrong. We do not want to leave square roots in the denominators. And again, I'll teach you in a few minutes how to clear them out. It's not that hard. Okay? But just make a note somewhere. Radicals in the denominator is just, politically incorrect. But so before we do that, let me just do a few more examples where we simplify things. How about we'll try a fourth root of 48 x to the power 9, y to the power 13, divided by a fourth root of 3x y to the negative second power. Ooh. So yeah, this is all messy, so let's just push it all together into the single radical and then simplify a fraction. That'll probably be the best way to go about this problem. So fourth root of 48 x to the power 9, y to the power 13, all over 3xy to the negative second power. So just push it all into one. Then I can start reducing this thing. 3 goes into 48 16 times, right? X cancels with x to the power 9, gives you the x to the power 8. Is that right? What's going to happen with the y's? How many y's do you have left? You have 13 on the top and negative 2 on the bottom. Y to the 15th, right? You subtract exponents. 13 minus negative 2 actually gives you 15. You're just adding 2 to the top. So what we have here is the 4th root of 16x to the power 8 y to the power 15. Okay, I wrote 16 for some reason. Said 15. I don't know why. 15. Because again, rules of exponents, you subtract exponent when you divide. So regardless, positive or negative, you're subtracting a negative number, so you're really making it a plus. So 16 the perfect 4th power to x to the 8th perfect 4th power. Again, divisible by 4. How about 15? What do we have to do to 15? Twelve and 3, right? You want it to be divisible by 4. So this is what we have. 16x to the 8th, and then y to the power 12 times y cubed. And this is the 4th root. Don't forget about that. So 4th root of 16 equals 2. 4th root of x to the 8th, you're just dividing by 4, is x squared. 4th root of y to the 12th, you dividing by 4 is y cubed. And we still have a 4th root of y cubed remaining. So this is as simple as it gets. Okay? Are we good? So this is kind of going back to what we did on Monday. So a few numerical examples. If I give you, I don't know, square root of 7 and I square it, what does that equal to? 7. Okay, good. What if I give you 2 square roots of 5 and I square that? What does that equal to? No. And? 20, because you square both. You square the 2, that's 4, and you square that, that's 5, so 20. Because it's a product, you square both parts of the product. Okay. If I give you a cube root of 3 and I cube it, 3. If I give you 2 square roots of 5 just times the square root of 5, what would that be? No. So I have a 2 times square root of 5 times square root of 5. What is square root of 5 times square root of 5? Which is 5, right? It's the same as square root of 5 squared, right? Or square root of 25. So this is 2 times 5. That equals 10, right? So there's a difference here. This is 2 root 5 times 2 root 5. This is just 2 root 5 times root 5. So only the square roots get squared. The 2 remains. How about 4 cube roots of 2 cubed? What will that be? That's a big number. $64. Okay, so 64 times what? What's the cube root of 2 cubed? 2. So 128. Okay. So you're cubing both parts. If I just give you 4 cube roots of 2 times a cube root of 2 like that, what would that be? No. Four cubed. No. Well, because square root of 5 times square root of 5 is 5. But the cube, I'm messing with you right now, but the cube root of 2 times cube root of 2 is just, yeah, so it's a, well, really what's happening, it's a cube root of 2 squared, right? It doesn't kill your power. This is really 4 cubes root of 4, right? You're squaring the 2. If I had that squared, then you would have 3 cube roots of 2, so that will give you a 2. Hang on a second, let me go back. Shut up, I'm not going to answer that question. That's okay. Your statistics teacher should be shot by a firing squad.
No, he said like.
No, I don't care. Stop it. Let's stop it. Let's stop it. Let's focus on this. Do we see why that cube root didn't go away? Well, because in order for the cube root to go away, I need a power 3, right? So I need 3 of those things in order for the cube root to go away. I only have 2, right? Because I mean, if I had cube root of 2 cubed, that is 2, right? I only have cube root of 2 squared, so that's something ugly, right? Okay. So if we had that, then it would have worked. Because you want this power to match that power. That's what kills the radical, right? Does that make sense? That's what I need. I don't talk about statistics right now. What? No, it doesn't equal 8. It equals whatever this ugly number is. Right. I would need 4 of them. So if I would give you this problem, let's say I have a 4th root of, I don't know, of 3, okay? And I would ask you, what is this? What do you have to multiply this by in order for all the radicals to go away and have just a pretty integer answer? So you were just saying that. So you need 3 more of this, right? You would have to multiply by the 4th root of 3 cubed. So that will give you the 4th root of 3 to the power 4, which is 3. Right? You want this power to match that power. Yeah? So I got both Ryans with me. Both Ryans are with me. Lost Sabrina. Eric is doing statistics. That's okay. I'm mad at you right now. I'm not talking to you. How about, I'm not talking to you. How about Sarah's? How are you doing? Okay. All right. So anyways, now if I give you this example, and we did that last time, 5 minus the square root of 2, 5 plus the square root of 2. So that was the very end of the Monday's packet, or whatever you call those things. How did we handle that problem? How do we handle any type of multiplication where you have 2 parentheses, one is a negative, one is a positive? What? Quick multiplication, which one? Difference of squares. This is using the difference of squares formula, gives you 5 squared minus the square root of 2 squared, right? That's your difference of squares formula. A minus B, A plus B is A squared minus B squared, right? Now, what does that equal to? What is 5 squared? 25. What is square root of 2 squared? 2. What is the result? 23. 23 is a pretty natural integer, whatever you want to call that, right? So every time we're going to multiply expressions, that contains square roots. Let's say square root of 7 plus square root of 3, and I'll multiply it by square root of 7 minus the square root of 3. We call these terms conjugates, the terms that only differ by a sign in the middle. Every time you multiply them, the answer will always come out a pretty integer result. Because again, if I apply the same formula, square root of 7 squared minus the square root of 3 squared, difference of squares formula. So what does that equal to? 7 minus 3, which is 4. Okay? Does that make sense? Okay. That's all right. We'll deal with that later. But that makes sense, right? It's okay. Okay. So, all right. What? Now, how about this one? Square root of 7 plus square root of 3 quantity squared. And again, for those of you who were here on Monday, you might have noticed something, that this question is different from the one above. How do you square a sum? Difference of sums? Yeah, that one. The a squared plus 2ab plus b squared. Every time we square a sum, you have to operate with that. So square of a sum, that's what we call it. We'll call them as we see it. So this will be square root of 7 squared plus 2 times the square root of 7 times the square root of 3. This is your 2ab plus the square root of 3 squared, right? The a squared, 2ab, b squared. Now, what is the square root of 7 squared? 7 plus square root of 7 times square root of 3, well, it's just square root of 21. I can push them together by whatever rules we just did. What's the square root of 3 squared? 3. So 7 plus 3 is 10, and plus 2 square roots of 21. Nothing else I can do with that. Those are not like terms. That's my answer. Right? So the point here, if you have a number kind of like that, you have a square roots separated by a plus. If you simply square that, you're still going to end up with square roots. Right? So you had a pair of square roots or whatever, you square that, you still have the square roots left. But if you multiply the conjugates, that's what we're going to call them from now on, two expressions that differ by a sign, that utilize a difference of squares formula, you're going to end up with a pretty natural number. Okay? So we'll keep that in mind, because now what we're going to do this thing that's called rationalizing the denominators. So this is what I was talking about 10 minutes ago, whatever, that we do not like seeing radicals in the denominators. Okay? So for example, you do the work and your answer comes out to like 1 over the square root of 2, and you put it in my math lab, or you put it on the exam or whatever, doesn't matter, you get marked wrong for that answer. Especially on my math lab. That's going to drive you crazy. You're going to redo the problem 17 times, and it comes out to be 1 over square root of 2 each time, and you put it in, gives you the wrong answer. Okay? Because we don't like seeing square roots in the denominators. Now, from that previous fun exercise that we did over here, you know, all of that, all those problems, what would make that square root go away? Multiply by square root of 2. So you want to have, basically the idea is the way that one goes away if I have a square root of 2 squared. And the way you obtain that is by multiplying by the square root of 2. Now, if you multiply the denominator by the square root of 2, you also have to multiply the numerator by the square root of 2. That's the only legal operation we can do on a fraction, multiplying it by 1. So this ends up being square root of 2 over square root of 2 squared, which is just 2. So that's root 2 over 2. So this is an acceptable answer. It is numerically the same as 1 divided by the square root of 2. Let me show you that. If I go 1 divided by the square root of 2 equals that, right? That's what we started with. And if I type in square root of 2 divided by 2, I get the same result. So they're numerically the same, but the second one is a lot easier to work with in the future. I mean, this is a much friendlier fraction because it has an integer denominator, okay? And I'll show you an example where you really get to appreciate the fact that the denominators are pretty. So how would we deal with 3 over square root of 11? Yeah, so multiply by root 11 over root 11. So that gives you 3 square roots of 11 over square root of 11 squared. So that's 3 root 11 over 11. Right? Oh, I know. I'm not saying it's hard. Okay, so but keep that one in mind. So if I go back to the problem we kind of did a while back, that one, if you multiply this by root 2 over root 2, you'll get the same answer as we were getting before. If you rationalize this denominator by multiplying by square root of 2 over the square root of 2, you get 2 in the denominator cancels with the 2 in the numerator, and you still have a root 2 left. So you still have the same answer when you rationalize that. Okay, so what if I have 5 over a cube root of 2, and let's have a 2 squared already. No. Well, but again, what do you mean by the same thing? Well, you're trying to match the powers. You have a 3, you want a 3, you have a 2. What are you missing to get a, because you want to have 3 and a 3, you have 3 and a 2. You just need one more. So you have to multiply by cube root of 2 over cube root of 2. So you have 2 squared and another 2, so it gives you 2 cubed. So then it works. So it's 5 cube root of 2 over cube root of 2 cubed. So that's 5 cube root of 2 over 2. So you already had 2 to begin with. You added one more. Right? Well, if it's just cube root of 2 to begin with, what you want is a cube root of 2 cubed. That's what you want. Then you're going to get a little 2 in the bottom. So the question is, well, what are you missing? 2. So you want to do cube root of 2 squared over cube root of 2 squared. So this is why the powers match. So really what you just multiplied, you multiplied by cube root of 4, right? I mean, that's what cube root of 2 squared is, right? Two squared is a 4. So again, you want those powers to match. So if I have 7th power, I mean 7th root of 2 cubed, so you have to bring 7th root of 2 to the 4th, so they match the powers. Okay? So this is really weird. Well, how about this fun exercise? 1 plus the square root of 2. So 1 over 1 plus the square root of 2. Mhm. So 1 plus the square root of 2. What should I multiply 1 plus square root of 2 by in order for all the square roots to go away? No. Because see what happens. That's what Eric suggested, right? If I multiply by root 2 over root 2, don't write this down, I'll get square root of 2, but then this distributes and still gives me 2 square root of 2 plus 2, so I still have a square root on the bottom, right? So that's not good. So what was I saying? When you have a sum or a difference, in order for the square root to go away, how do you turn that into a pretty number? The previous discussion that we just had on the previous page of your notes. Do you see something like that? A sum and a difference multiplied by something gives you a pretty answer in the end? No. Look at the last few computations that we did. When do you get a pretty answer? Would be minus. Right, I want to have the opposite signs. I want to achieve the difference of squares effect. If I multiply by the same thing, I'll achieve the square of a sum effect, so I'll still have a square root left. The only way you kill a square root that's a part of the sum is by multiplying by conjugate. And the conjugate means just change the sign in the middle. Okay? So when you're faced with this types of situation where you have 1 plus the square root of 2, multiply by the same expression only with the opposite sign. This way, the difference of squares formula kicks in and it kills that little radical. Yeah. Yeah. That's a C. Okay, let me try it again. It just, so conjugate. So this way you have 1 minus square root of 2 over 1 squared minus the square root of 2 squared. Right? Difference of squares formula. So that squares each item individually and it kills the square root. This is why we were paying so much attention to the differences of squares formulas and so forth. And that's why the foiling was frowned upon, because you have to realize what happens there. So it just gives you a -1. Both of those are the same. So when you have a sum or difference in a denominator that involves at least one square root, multiplied by the conjugate, meaning the opposite sign. Just change the sign. That's all it takes. Well, 1 minus 2 is just -1, so just made everything negative, right? Or so you distribute the negative, it just flips the whole thing. All right, so let's try the, what? Why not? Well, you haven't used it yet. Why does it hurt? You were just copying everything down. Your hand hurts, maybe. So want to, compute that, evaluate. So 3 fractions, and as you know, when you add fractions, you have to have, no. So in order to add fractions, what do you need to do in order to add fractions? Yeah, the denominators have to be the same. Find the least common denominator. These three denominators are very different. So the LCD would be the product of all three. The LCD, as it's written, is square root of 7 times square root of 7 minus square root of 5 times whatever that last one is, square root of 5 plus 3. That's a huge LCD. That means the first fraction has to be multiplied by square root of 7 minus square root of 5 times square root of 5 plus square root of 3, whatever on earth that is, and so forth. You get the gist? This is miserable problem, right? Or we should probably rationalize those denominators. Because if we rationalize the denominators, the whole LCD issue is going to be a whole lot easier, not as extreme as it is right now. So this is bigger reason why we want to do that. So rationalize the denominators. So I'm going to take one separately, one by one by one. So how do we rationalize the first one? That should be pretty easy, right? How do we do the first one? So root 7 over root 7. Is that right? That's how we rationalize that. So I'm just going to write it as 7 square roots of 7 over root 7 times root 7 is another 7. Is that okay? 7's canceled because these are all products, and that's a square root of 7. So the other one, 2 over square root of 7 minus square root of 5. So I want to rationalize that denominator. What do I have to do? Square root of 7 plus square root of 5. I want to go for the conjugate. So square root of 7 plus square root of 5 over square root of 7 plus square root of 5. So in the numerator, it is 2 times the square root of 7 plus the square root of 5. In the denominator, the difference of squares takes over. So that's a square root of 7 squared minus square root of 5 squared, which is 7 minus 5. Do you all agree with that? The denominator is just 7 minus 5, which is what? What is 7 minus 5? 2 over 2, so 2's cancel, so we get square root of 7 plus square root of 5. No denominator. And do the same thing to the third one. 3. So what do we have there? It's 4 over square root of 5 plus the square root of 3. So what do I multiply that one by? Square root of 5 minus square root of 3. We're going for the conjugate. So this is 4 times the square root of 5 minus the square root of 3 over difference of squares gives me square root of 5 squared minus square root of 3 squared, which is 5 minus 3, which is 2. So I have a 2 in the denominator. So we have 4 times square root of 5 minus square root of 3 over 2, which is 2 times root 5 minus root 3. Well, it's because this is just 5 minus 3, because the squares, yeah. Is that okay? So if we do that first, which still feels like a lot of work, but it's nowhere near close to what would happen if you try to add those straight up. But let's see what we have. The first fraction is just square root of 7. That's the first one, right? The second one, I have to subtract. The second one, I have to be a little careful. I have to make sure I'm subtracting the whole thing. So I do need parentheses around square root of 7 plus square root of 5. And then plus the last one, which is 2 times square root of 5 minus square root of 3. And again, the reason why I put parentheses around the second expression is that because that minus in the original problem, I have to make sure that the whole thing gets subtracted. So every time you're subtracting an expression, put in a parenthesis. So we've mentioned this many, many times. Well, that's a lot better, right? If I open up all the parentheses, this is just square root of 7 minus square root of 7 minus square root of 5 plus 2 square root of 5 minus 2 square roots of 3. So what are we left with? For those first two cancel, that's for sure. So you have negative plus 2. No. Square root of 5. No, you can combine these two. That's negative square root of 5 plus, so leaves you with 1. Minus 2 square roots of 3. So that's the answer. I'm never going to show you what it looks like if you don't rationalize it. It's unholy mess. Yeah. Yeah, I know. Radicals. Okay, good. Well, I think, yeah, we're all kinds of out of time.